More L'Hopital's rule. So, and I said last time, I'm going to say it again. There's only two instances where you actually are allowed to use L'Hopital's rule. So you have to have something like this. You have to have either, so if we have, I know I said this last time, but I think it's worth repeating. So if we have the limit as x approaches a of f of x over g of x, and it's either a 0 over 0 type or some sort of infinity over some sort of infinity, then we get to say that the limit as x approaches a of f of x divided by g of x is equal to, as long as it exists, the limit as x approaches a of f prime of x divided by g prime of x. So whenever you see a limit that appears to be an indeterminate form, you have to check it's one of these two things, and only after you've at least internally checked, then you can use L'Hopital's rule. So for example, the limit as x approaches 0 from the right of cosine x over x is not a time you can use L'Hopital's rule. So you plug in 0, you don't get 0 over 0. You get 1 over 0. And in the past, we've seen that when you have a limit like this, you can evaluate it by, well, specifically a not 0 over 0 type of limit. That's going to be some sort of infinity. We know that the top is getting closer to 1, the bottom is slightly positive, so the overall result is going to be a positive infinity. And similarly, if you wanted to look at it from the other side, I know these aren't examples of L'Hopital's rule, but I just want to emphasize here, you can't always use L'Hopital's rule without, you can't blindly just be like, oh, cool, L'Hopital's rule, I see a fraction. No, you have to make sure it's the right kind of thing. So if you had the limit from the left, it also would not be applicable. You'd still get a 1 over a 0. This time it would be a negative infinity. So all I'm really trying to make sure you say is when you have your final exam and you have limits on your final exam, which you definitely will, make sure before you apply L'Hopital's rule that you're actually permitted to do so. Also, last time, I said L'Hopital's rule, and I'm like, here's all these examples where you shouldn't use L'Hopital's rule, but that's good to know. So here's another example. Here's a different example where you could, but you shouldn't. And I talked about this one kind of last time, but I'm going to give you the more terrible one now. If you had the limit, let's say x approaches 0 of sine cubed of 5x divided by 9x cubed. I dare you to use L'Hopital's rule here, but you shouldn't. Like you should not take that dare. It's a terrible dare. Like the second, like the first time is okay. The second time is pretty gross. The third step, because you have to do L'Hopital's rule 3 times here, is heinous. Don't do it. Instead, go back to the old school way of doing this and break it up as the limit as x goes to 0 of sine of 5x over blank times sine of 5x over blank times sine of 5x over blank times blank over 9x cubed, and then fill in what you want. So you want a 5x here, a 5x here, a 5x here. We need a 5x times 5x times 5x, or a 5x cubed over there. And then when you evaluate this, you just end up getting 1 times 1 times 1 times the x's cancel over here, and you get 5 cubed over 9 for a final answer of 125 over 9. This is so much easier than trying to use L'Hopital's rule. It's ridiculous. Papers. Okay, cool. Let's see. Yeah, let's look at this one. Sure. Let's try the limit as x approaches 0 of the natural log of e to the 2x minus 1 over the natural log of x. Can we use L'Hopital's rule here? That should always be the question. Like, so at this point, when you see a limit, not that we always have to use L'Hopital's rule, but your question should always be, am I allowed to even use it? Well, let's check. If we plug in 0, right, plug in 0, we get, on the bottom, we get the natural log of 0, which I know doesn't exist, but I'm writing it just for my own sake here. On the top, e to the 0 is 1, 1 minus 1 is 0, not, so we also get the natural log of 0. which is what kind of indeterminate form? What's the natural log of something really, really close to zero? Right. We got a negative infinity. Cool. So it's an infinity over infinity type. We definitely can use L'Hopital's rule. So yes, we can use L'Hopital. So then we rewrite this. We say it's equal to, I appreciate this notation. Excuse me here. Your L apostrophe H to show that you're actually using it. Still write the limit. You have to write the limit. It's not L'Hopital's rule without a limit. They both start with L, right? You got to have an L thing. And now, okay, the bottom's easier. Let's do that first. The derivative of natural log of x is 1 over x. The derivative of e to the 2, sorry, the natural log of e to the 2x minus 1 is 1 over e to the 2x minus 1 multiplied by the derivative of that, which is e to the 2x times 2. And it doesn't look good if I plug in, like plugging in 0 right now seems terrible. Like I don't really even want to think about it. I definitely think when you have fractions and fractions, it's usually worth simplifying before you even try to think about plugging in. So what I'm going to do is I'm going to rewrite the top as 2 e to the 2x over e to the 2x minus 1, and I'm going to multiply by x over 1. So I'm going to rewrite this as the limit as x goes to 0. I have my 2e to the 2x over e to the 2x minus 1. And instead of multiplying by x out here, let's put the x on top as well. So I have a times x on top. And now let's ask ourselves what happens when we plug in 0. Well, on top, we're going to get 2e to the 0 times 0. So that's going to be a 0 on top. On the bottom, e to the 0 minus 1 is 1 minus 1, which is 0. So we still have a form where we can use L'Hopital's rule. So we keep using it until we can't use it anymore. Yeah. That's generally good advice. Sometimes, so I should say, sometimes you could use it again, but simplifying is a better choice. So maybe not always keep using it. Maybe check to see if you can simplify in a way that's useful before you just blindly keep going. So taking the derivative of the top and the bottom, let's see. I have the limit as x goes to 0. The derivative of the bottom is e to the 2x times 2. The derivative of the top, I have to use the product rule. So I'm going to think I have 2e to the 2x times x. So it's going to be the derivative of 2e to the 2x, which is 4e to the 2x times x left alone, plus, now I'm going to leave the 2e to the 2x alone and multiply by the derivative of x, which is 1. And now it looks like I should be able to get a real number result because when I plug in 0, the bottom certainly isn't going to be 0 or infinity. It's going to be 2. So plugging in 0, I get 4 times e to the 0 times 0 plus 2 times e to the 0 times 1 divided by 2 times e to the 0. And then I'm getting 1. Interesting. Let's see. What else do I have? Sure, let's try that one. Why don't you all give this one a shot? Yeah, let's just be careful with my paper choices here. To try the limit as x approaches 0 of sine x minus x divided by x cubed. And yes, you definitely can use L'Hopital's rule in the first step. Give that a try. let's go ahead and take a look. So it is a 0 over 0 type. Sine of 0 is 0, minus 0 over 0 cubed. If we use L'Hopital's rule one time, we now have the limit as x goes to 0 of cosine of x minus 1 over 3x squared. And if we plug in 0, we still get 0 over 0. This is going to happen a lot, by the way. When you're going to have problems where you have to apply L'Hopital's rule like 2 or 3 times, not infrequently. So definitely you should always check, like before you just try and do it again, right? You should always check before you use L'Hopital's rule, but often you'll get another 0 over 0 or another infinity over infinity. So using this again, let's see, we get, using L'Hopital's rule again, we get the limit as x goes to 0. The derivative of cosine of x is negative sine of x. The derivative of negative 1 is 0. The bottom is going to be 6x. And again, we see a 0 over 0 type. At this point, you probably could just say the answer is negative 1/6 because you know that the sine x over x part has a limit that's 1. But if you've already used L'Hopital's rule twice, you might as well just do it again. And you get negative cosine of x divided by 6, and then you plug in the 0, and you get negative cosine of 0 over 6. Let's look at another one. Let's look at, say, the limit as x approaches 0. Where'd you go? I had you right in my sights. Oh yeah, here we go. X minus sine of x over tangent x minus x. Interesting. Tangent of 0 is 0. So this is definitely a 0 over 0 type. So let's see what happens here, because there's something to be learned here. I mean, there's always something to be learned, but there's something specific. So if we use L'Hopital's rule one time, bless you, the derivative of the top is going to be 1 minus cosine of x. The derivative of the bottom is going to be secant squared x minus 1. Interesting. I hadn't thought about that. And here we see that if you plug in 0 again, you still get 0 over 0, because cosine of 0 is 1 and secant of 0 is 1. So we can use L'Hopital's rule again, and I think we should. Yeah, I think we should. I probably think we should. You could probably do some manipulation here if you wanted to, but that's kind of dependent upon how comfortable you are with trig identities and manipulating trig things. So I think it's a safer route to use L'Hopital's rule again here. So we're going to use L'Hopital's rule again. The derivative of negative cosine is positive sine. The derivative of secant squared, we have to be a little bit careful, right? That's secant of x quantity squared. Its derivative is 2 times secant of x to the first times the derivative of secant, which is secant of x times tangent of x. And this is where if I plug in 0, I do still get 0 over 0. Right? Secant, sine of 0 is 0, tangent of 0 is 0, and it doesn't matter that secant of 0 is 1. No, it's not yet. And this is where I'd be hesitant to try to use L'Hopital's rule again, because taking the derivative of the bottom is going to be kind of gross. This is where it might be good to kind of think about how I could rewrite things. So if you take a moment here, tangent is really just sine divided by cosine. So I could rewrite this as the limit as x goes to 0 of sine of x over 2 secant of x, secant squared of x, if I'm smart about it, times sine of x divided by cosine of x. I can bring that cosine x up to the top, and the signs get to cancel. So I can rewrite this as the limit as x goes to 0 of cosine of x over 2 times secant squared of x. That seems much easier than using L'Hopital's rule again. And then we plug in 0, and we get cosine of 0 over 2 times secant squared of 0, which is just 1 over 2. Cool. Patterns. Where's the other one? Sure we do. All right, so it's great if your thing you're taking the limit of is already a fractional form. But sometimes it's not, or at least doesn't start off as being a single fraction. Oh, there's one. There is a problem. I'm trying to remember a problem that I like, but I can't remember what it is exactly. Oh, well, it's fine. I've got lots of problems. So let's look at this example here. Yeah, was I numbering things? I probably already, let's see. Are there numbers? Yes, there's numbers. Let's try to keep the numbers. Number 7. So we want to find the limit as x goes to 0 from the right of 5x plus 1 over x minus 1 over tangent of x. Now this looks a little different from the get-go. First of all, it's not just one fraction, so it's not infinity over infinity or 0 over 0 yet. Also, if we plugged in 0, which you should always think about, let's see what happens when we plug in 0. So for this one here, if I plug in 0, I get 1 over 0, and it's a slightly positive 0, minus 1 over tangent of a slightly positive 0, which is going to be a slightly positive 0, right? Because tangent of 0 is 0. If you think about the graph of tangent, if you're a little bit to the right of 0, your tangent value is a little bit positive. So this is also so essentially we have a positive infinity minus a positive infinity, which is an indeterminate form. Infinity minus infinity could be anything. The first infinity could be infinitely bigger than the second infinity. Or it could be 1 bigger, or 3 bigger, or -5 bigger, or 5 smaller, right? You could have any difference here. Now, one thing I want to point out, because I feel like students often miss this, infinity minus infinity is indeterminate. Indeterminate. Can I spell that word? Yes. So is negative infinity minus negative infinity, or as you might be more likely to write it, negative infinity plus infinity. But any other addition or subtraction of infinities isn't. So for example, just to point out here, infinity plus infinity is not indeterminate. If you take infinity, you add infinity, it's going to be infinitely large. And, and also negative infinity minus infinity. These are both not indeterminate. They are fully determined. We know that a big number plus a big number is a big number, or a negatively big number plus minus a big number is a negatively big number. So don't fool yourself into thinking that these are indeterminate. They are not. Here, we should do the smart thing and get a common denominator, right? If you're adding or subtracting two fractions, we should get a common denominator to make one fraction, right? You're always with limits where you think you might use L'Hopital's rule, you have to make it a fraction. You don't have a choice. There has to be a fraction to use L'Hopital's rule. I'm going to say it one more time. There has to be a fraction to use L'Hopital's rule. You cannot use it without a fraction. So to make that, I want to really, really emphasize that. So here, not too terrible. It's going to be the limit as x approaches 0 from the right. We have 5x plus 1 over x. We're going to multiply that by tangent of x over tangent of x. Similarly, over here, we're going to multiply our 1 over tangent of x by x over x. And now, when we write this out, if the limit as x goes to 0 from the right, on top, we're going to have 5x plus 1 times tangent of x minus x. On the bottom, we're going to have x times tangent of x. And here's the good news. The good news is if you start with an indeterminate form and manipulate it to look like a fraction, it will still be an indeterminate form, and it almost has to be like I think it has to be a 0 over 0 or infinity. You can't get something else. It has to be a 0 over 0 or some sort of infinity over some sort of infinity. There's no other result that can happen. Let's check. If you plug in 0, let's see. 0 plus 1 is 1 times tangent is 0. Tangent of 0 is 0. So we get 0 minus 0 over 0 times. So yeah, it's definitely a 0 over 0 type. So great. This is probably going to be ugly, but let's use L'Hopital's rule and see what happens. Limit x goes to 0 from the right. All right, you all do it. Take those derivatives. Remember, you're not using the quotient rule. You're just taking the derivative of the bottom and the derivative of the top. You will have to use the product rule, though. I'm worried this is going to get ugly. there's the problem I was looking for. Cool. Let's see. The bottom derivative is 1 times tangent plus x times secant squared. The top, a little bit grosser. The derivative of 5x plus 1 is 5. Leave the tangent alone. Plus, leave the 5x plus 1 alone. The derivative tangent of x is secant squared of x minus 1. And I'm not very confident, but I'm pretty sure it's going to be 0 over 0. So let's check. 0. Let's see. So so the bottom is definitely 0, right? Because you have a tangent of 0 and a 0 times whatever. I should say a 0 times not infinity, right? If that was an infinity there, you couldn't just say it's 0. So be a little careful. But it's usually not a problem. On top, let's see. This part's going to be 0. That's going to be 1 times 1. Yep, we get 0 plus 1 minus 1, which is still 0. So it's still a 0 over 0 type. Oh, now I'm a little bit worried this is going to get really gross. Oh well, sometimes things get gross. I probably need to not try to squeeze this. I can probably fit this in here. Let's see. So you get limit as x goes to 0 from the right. And okay. On the bottom, the derivative tangent of x is secant squared of x plus product rule over here. Interesting. Sorry, I'm just having a thought. One moment. No, that's kind of dumb. No, that's not better. Okay, so sorry. I'll tell you what my thought was after we finish this. Derivative of this, you're going to get 1 times secant squared of x plus x times the derivative of secant squared, which is 2, times secant to the first, times the derivative of secant, which is secant times tangent. Here's the good news before we do the top part. I'm pretty sure the bottom's not going to be 0 when we plug in 0, because you're going to get 1 plus 0. So the bottom's definitely going to go to 2. So good news, this is the last step. Almost definitely. Bad news, we still take the derivative of the top. It's not that bad. Okay. So it's pretty much the same as the bottom, right? It's just a little bit more complicated. So the derivative of 5 tangent to x is going to be 5 secant squared of x. The derivative of 5x plus 1 times secant squared of x, product rule again, similar to the bottom. It's going to be 5 times secant squared of x plus 5x plus 1 times the derivative of secant, which is, sorry, derivative of secant squared, which is 2 times secant of x times another secant times tangent, minus 0. And then we plug in, and if we plug in 0, we get 5 times 1 plus 5 times 1 plus 1 times 2 times 1 times 0. So we really get 5 plus 5, which is 10 on top. On the bottom, we get 1 plus 1 plus 0. So we get 2 on the bottom. So our final answer is 5. It's a lot of work for 5. So you can probably see being able to differentiate things quickly and accurately is super important for these problems, right? You have to be able to do the derivatives. Let's look at one more of this variety here. So let's look at the following. Let's look at the, I can't quite see that still. Cool. Let's look at the limit as x approaches 1 from the right of 1 over the natural log of x minus 1 over x minus 1. And you can see here that we still have an infinity over infinity type. As x approaches 1 from the right, natural log of 1 is 0, but it's a little bit bigger than 0, so you get 1 over a positive number. This is definitely an infinity minus a 1 over a number that's small and positive is going to also go to infinity. So we have an indeterminate form. All right. Go to work. Get yourself a common denominator, make yourself one fraction, and then use L'Hopital's rule. Water on this. There's another attendance form with water on it. Hmm, interesting. Oop, I'm gonna start writing stuff down. Let's see here. So there's a simplification. We get a common denominator. We got x minus 1 minus natural log of x over x minus 1 times natural log of x, and that's definitely a 0 over 0 type when you plug in 1. So now we use L'Hopital's rule. So we get the limit as x goes to 1 from the right. Taking the derivative of the top, let's see. We have 1 minus 0 minus 1 over x. Taking the derivative of the bottom, product rule as usual, not as usual, but again, we get 1 times natural log of x plus x minus 1 times 1 over x. I would check to see, like here, it's easy enough to plug in 1 to see what happens. I don't think we need to simplify yet. So plugging in 1, I get 1 minus 1, which is 0, over natural log of 1, which is 0, plus 0 times 1, which is also 0. So 0 plus 0. So it's still a 0 over 0 type. Now here's the thing. Yeah, how do I feel about this? Here's what I want to do. I want to multiply the top and bottom by x. I'd really rather not have fractions and fractions. I'm totally allowed to do that. But let's kind of see what happens both ways. I think it's kind of interesting both ways. So one way, I'm gonna just simplify the denominator here before I do the derivative, before I use L'Hopital's rule again. So I rewrite this way. Its limit as x goes to 1 from the right. I have 1 minus 1 over x on top. On the bottom, I have natural log of x. And if I distribute the 1 over x, I have x times 1 over x is 1, minus 1 times 1 over x is minus 1 over x. And if we use L'Hopital's rule, we're going to get the limit as x approaches 1 from the right. The derivative of the top is going to be 0 minus. I would encourage you all to know the following without having to rewrite it. The derivative of 1 over x is negative 1 over x squared. It's going to happen a lot. So just get used to it. Yes, you can rewrite it. You can write 1 over x as x to the negative 1, and then the derivative is negative 1 times x to the negative 2, and you can rewrite that as negative 1 over x squared. But I definitely think it's worthwhile to know that the derivative of 1 over x is just going to be negative 1 over x squared. Comes up frequently in L'Hopital's rule problems. Okay, on the bottom, the derivative of the natural log of x is 1 over x. The derivative of 1 is 0. The derivative of negative 1 over x is positive 1 over x squared. So plugging in 1, we get positive 1 over 1 over 1 over 1 plus 1 over 1. So we get 1 half. Okay, that wasn't too bad. What I wanted to do, and maybe this is not the best intuition, but what I saw was I could multiply the top and bottom by x. On top, if I multiply the whole thing by x, I get x minus 1. On the bottom, if I multiply the whole thing by x, I get x natural log of x plus x minus 1. Is that better? I don't know. Probably not. But sometimes your intuition just tells you to do a thing. So then if I use L'Hopital's rule here, derivative of the top is 1 minus 0. The derivative of the bottom, I don't use the product rule, so that's probably not better. But using the product rule, I get 1 times natural log of x plus x times 1 over x plus 1 minus 0. And plugging in 1, I'm going to get 1 over natural log of 1, which is 0, plus 1 times 1 over 1, which is 1, plus another 1. I still get 1 half. So it is totally okay to do that simplification where I multiply the top and bottom. Right? I multiplied by x over x. But it probably wasn't super necessary. I just saw, I don't always love having fractions and fractions. That's kind of my go-to is, fraction, let's not. I think honestly, what I really kind of saw in my head, to be perfectly frank, was I'm used to my limit being x approaching 0. And so to me, 1 over x kind of just inherently felt problematic, even though it wasn't. Okay, let's look at some other varieties of indeterminate forms. Let's look at, say, so far, so just as a, yeah, so before we write this down, so far, our indeterminate forms consist of the following: 0 over 0, either type of infinity over either type of infinity, infinity minus infinity. Or I guess if you really like, negative infinity plus infinity. Although that's just really just rearranging the way you're adding or subtracting things, right? If you had negative infinity plus infinity, you could just write the second thing first and the first thing second, and then you'd have that there. So those are pretty interchangeable. There's still a few more though. In fact, there's like, I don't know, 4 more, 5 more. We'll come back to that. Sorry, I'll leave that up there. I should also point out, when we say 0 divided by 0, that's not what we really mean. We mean a number that's really small divided by a number that's really small, which is why it's okay that sometimes it's 5 and sometimes it's 37 or a billion or infinity, right? There's lots of possible outcomes. Literally anything. That's why it's indeterminate. So let's look at the next example. The limit. Do I still have numbers? Did I abandon the numbers? Am I still writing numbers? I am. Good job. Okay. Number 9. The limit as x approaches 0 from the right, and here it's kind of necessary from the right, of x to the 6th times the natural log of x. You can't approach 0 from any other side because the natural log of x is only defined when x is positive. So this, if we actually plug in 0, let's see what happens. We get 0 to the 6th, which is still 0, times the natural log of 0, but that's essentially a 0 times a negative infinity. Or as we said last class, because we did talk about one like this last class, you have a small thing multiplied by a very large thing, very negatively large thing. We don't really care about the sign so much. So if you have a small thing times a big thing, which thing wins? Sometimes the big thing wins and you get something infinite. Sometimes the small thing wins and you get something that's 0. Sometimes they balance in a way where you get something in between, like -4, which is not the answer here, but it's possible to get something like that. So let's see what happens here. I would say a lot of the times for these problems, you do get something like 0. Like 0 is often the answer for problems like this. Usually there's a lot of the times there's a clear like winner. The bigger thing wins or the smaller thing wins. There's rarely a balancing in my experience. Maybe I just don't come up with very original problems. Anyway, let's not use L'Hopital's rule right away because we can't. So we need to rewrite this. And here's where you have a choice, and there's almost always a preferred choice. You can rewrite this as a fraction in one of two ways. You can either write it as the limit as x goes to 0 from the right of x to the 6th divided by the reciprocal of the other piece, or you can write it as the limit as x goes to 0 of natural log of x divided by the reciprocal of the other piece. And your guiding principle here should be that the thing that ends up in the denominator, you want it to be something that simplifies easily or you take the derivative of easily. Natural log is never the choice. You never want to put natural log in the bottom as 1 over natural log of x. And then taking the derivative of that, you can either write it as natural log of x to the -1, and the derivative is going to be gross. It's going to be -1 natural log of x to the -2, right? That's terrible. Or this one is really easy. That becomes x to the -6, and that's easy to differentiate. So this is definitely the way to go, not this. Will it still work if you do it this way? Sometimes, not always. Sometimes you do it, you go the wrong way, and the path is getting worse and worse and worse. I'll show you a different example where that happens. This is not the best example for that. Here, we're going to do this way. So it does pay to rewrite this as the limit as x goes to 0 from the right of the natural log of x over x to the negative sixth. I'd rather not have to use the quotient rule if I don't have to. So, one sec. Sorry, I do need to answer this. Okay, so now we can use L'Hopital's. Oh, I should have pointed out we can use L'Hopital's rule here, right? Because here, natural log of 0 is a negative infinity, and 1 over 0 is in this case, a positive infinity. So we definitely have an infinity over infinity type. They don't have to be the same sort of infinity. It's totally fine that one of them is going to negative, one's going to positive. Totally, totally fine. So now we can use L'Hopital's rule. We have the limit as x goes to 0 from the right. The derivative of the top is 1 over x. The derivative of the bottom is negative 6x to the negative 7th. Here is a place where you could keep going incorrectly. If you chose to, let me just show you, don't write this part down. I mean, you can, I guess, but I don't think you need to. If I rewrote this as 1 over x over negative 6 over x to the 7th, you could say to yourself, well, look, that's still an infinity over infinity type, right? The top's going to positive infinity, the bottom's going to negative infinity. And you could apply L'Hopital's rule again, and you shouldn't. So if you do it again, you're just going to get stuck. For here, this is x to the negative 1, this is x to the negative 7. If you take the derivative, you're just going to get more and more negative powers of x, right? If I were to go again, really, we don't want this, but if we incorrectly did L'Hopital's rule again, here's what's going to happen. Your limit as x goes to 0 from the right of x to the negative first over negative 6 to the x to the negative 7th is going to be the limit as x goes to 0 from the right of negative x to the negative 2 times over positive 42 to x, right? Your powers are just getting more and more negative. There's no end to that process if you're not careful. The smart thing to do here is to recognize, hey, we got a bunch of powers of x. We can definitely simplify that. So what we should do here instead is say, look, this is the limit as x goes to 0 from the right of 1 over x times the reciprocal of negative 6x to the over x to the 7th, which is x to the 7th over negative 6. And then things become relatively not terrible. Simplifying, it's the limit as x goes to 0 from the right of x to the 6th over negative 6, and then we can just plug in 0. You get 0 to the 6th over negative 6, which is just 0. What I kind of think about for a problem like this is a natural log of x. I don't really want to say that. No, I don't like that at all. Never mind. I have nothing good to say here. Natural log of x goes to infinity really slowly. So x to a power usually goes to 0 faster than natural log of x is kind of able to overcome how fast it goes to 0. Let's look at another example. Yeah, let's do that one. Let's say there was something I wanted to make sure I said here. Yeah. Let's look at the limit as x goes to infinity of x squared times e to the negative x. Yeah, which I think we did one similar to this last time. It's okay. So again, same sort of thing happening here. If you plug in infinity, you're going to get infinity times e to the negative infinity, which is essentially an infinity times 0. Here's the example where I want to show you where you really can go the wrong way here. So check this out. So here's the wrong way. Bringing the x squared down to the bottom. If you rewrite this as the limit as x goes to infinity of e to the negative x divided by the reciprocal of x squared, or preferably, so it's easier to take the derivative of each part, the limit as x goes to infinity of e to the negative x divided by x to the negative 2. This is going to be a never-ending process, because if we use L'Hopital's rule, we're going to get the limit. Oh, I should say, first of all, before I use L'Hopital's rule, I can see that if I plug in infinity here, I do have a 0 over 0 type. E to the negative infinity goes to 0. 1 over infinity squared goes to zero. So it's definitely a 0 over 0. I will repeat myself here. If you started with an indeterminate form, like infinity times 0, and made it look like a fraction, there should never be a question of it being a 0 over 0 or an infinity over infinity. It's always going to work. It's still a good idea to check. So here, if we use L'Hopital's rule, look what happens. The derivative of e to the negative x is negative e to the negative x. The derivative of x to the negative 2 is negative 2 over x to the negative third. That's not good. The negatives cancel, sure. You can write it as the limit. I'm going to rewrite it as, interesting here, 1 over e to the x over 2 over x cubed. Yeah, it's a 0 over 0, and it's not going to get better. If I write the power on the bottom, it's going to keep getting more and more negative. This is the wrong way to go. You don't want to put the x squared on the bottom. So what I would say is the thing that should go on the bottom is the thing that doesn't get more complicated when you start differentiating it. Like in this case, that's not really a good guideline either, though. I don't have a good way of saying it, right? It's the thing that's going to be better. How helpful, right? But in this case, it's much better to put the e to the something on the bottom because the derivative of e to the x is just e to the x. And leaving the x squared on top, the derivative will make the power of x squared get less, not greater. So instead, the right way to do this is to write it as the limit as x goes to infinity of x squared divided by the reciprocal of e to the negative x. Now, normally I would just skip right by that step and write it as the limit as x goes to infinity of x squared divided by e to the x. And now it looks like it's going to be not that terrible. We're going to use, it is an infinity over infinity type. It is worth noting that whichever way you do it, one way will give you a 0 over 0, and one way will give you some sort of infinity over some sort of infinity, right? Because when you bring down the x squared, when you bring down the reciprocal of x squared to the bottom, you're getting a 1 over an infinity. When you bring down the reciprocal of e to the negative x to the bottom, you're getting a 1 over a 0. And those are kind of opposite things. So here, using L'Hopital's rule, we get the limit as x goes to infinity of 2x over e to the x. It's still infinity over infinity, so we do it again. We get the limit as x goes to infinity of 2 over e to the x, and then we can see that, oh, we're going to get 2 over something infinitely large, which is 0. So, see. Oh, I had one. Yeah, that's fine. Sure. Where'd you go? Sorry, sometimes my brain just loses things here. Oh, there it was. Yeah. Sure. How about this one? This is kind of interesting. Oh, numbers. Did I lose my numbers? 9, 10, 11. Sure. The last one was 10. How about the limit as x approaches 0 of e to the 3x minus 1 times the natural log of x? Seems terrible. But it's still the same sort of format. If you plugged in 0, you'd have e to the 0, which is 1 minus 1. So you have a 0 times a negative infinity. Ugh. So this question, this is going to be kind of gross. I'm not going to lie. I still am going to stand by. So here's the truth. I don't know which way I should go here. You usually don't know what you should do until you've done it a few times. My gut reaction here is never put natural log in the bottom. You don't want 1 over natural log of x. It's just terrible. There's another place for that too. I feel like somehow that applies to 21b somewhere when you talk about integration by parts or something, but whatever. That's not where we're at. So leave the natural log of x in the numerator, but that means this is not going to simplify very nice in the denominator. So here's unfortunately what we're stuck with. The limit as x goes to 0, natural log of x on top, the reciprocal of e to the 3x minus 1 on the bottom. And unlike the previous one where you had 1 over just e to the negative x and it became e to the x, that's not going to happen here. You have a choice. Your choice is to either just use the quotient rule when you take the derivative of the bottom part. I think it's probably a better idea to write it as the limit as x goes to 0 of natural log of x over parentheses e to the 3x minus 1 to the negative 1 power. I think I'd rather use the chain rule than the quotient rule, but it really matter of preference. If you like the quotient rule better here, use the quotient rule for the bottom part. It's really up to you. Okay, so I don't really need to check, but I'm going to check anyway. I plug in 0. Oh, there should be a 0 from the right. Yeah, that's actually what it did say. And it has to be a 0 from the right because, again, of the natural log of x function there, right? You're not defined on the left side of 0. So just to check, natural log of 0 is going to negative infinity, and 1 over e to the 0 minus 1 is 1 over 0, which is going to some sort of infinity, probably a positive infinity. Cool. So it definitely is, again, didn't need to check really because we had an indeterminate form to start with and we manipulated it, but still. All right, let's throw L'Hopital's rule out and see what happens. Ugh. On top, easy, 1 over x. On the bottom, not as easy. It's negative 1 times e to the 3x minus 1 to the negative 2 times the derivative of the inside part, which is going to be e to the 3x times 3. Ugh. This is definitely a time where simplification is what we should do. So let's go ahead and rewrite this as the limit as x goes to 0 from the right. Let's just bring this e to the 3x minus 1 to the negative 2 up to the top as positive as e to the 3x minus 1 to the positive 2. And also let's bring the 1 over the x down to the bottom here. So let's be super careful here. I'm going to have my e to the 3x minus 1 squared on top. On the bottom, this negative 3, fine, sure. This x I'm going to bring down to the bottom, right? Because again, really, this is x to the negative 1, which I bring down to the bottom is x to the positive 1. And then my e to the 3x is still hanging out there. It should still be, well, I should try plugging in, right? I should always at least think about plugging in after I've done L'Hopital's rule. I didn't really want to do it in the previous one though, because it just looked ugly. If I plug in here, I get e to the 0, which is 1 minus 1, so I get a 0 on top. On the bottom, 3 times 0 times e to the 0 is 0 times 1. So yeah, it's a 0 over 0. So we keep going. But I do think this is probably the best way of writing it so I don't have anything too terrible going on in either part. I think. Let's try. Let's see what happens. I should kind of reinforce though, a lot of doing this is trying something that you're not sure maybe is going to work. I'd say that's especially true next quarter in 21B when you start doing integration. A lot of integration is trying something that you're not sure is going to work. And then when it doesn't work, trying something else. Get accustomed to trying things that might not work. It's okay to go down the wrong path and then abandon it. Just try not to abandon it too soon. Like you want to give it your best shot. Be like, okay, this seems like it's not going where I want to go. Here, let's see what happens. So derivative of the top part, 2 times our e to the 3x minus 1 times the derivative of the inside, which is 3 e to the 3x. That's cool. That's probably going to cancel out somehow. Maybe. On the bottom, product rule, I'm going to think of it as negative 3x times e to the 3x. So the derivative of negative 3x is negative 3 times the other piece plus the negative 3x times the derivative of the other piece, which is 3 e to the 3x. And it, to me, it seems worthwhile to factor and cancel an e to the 3x, but it might not be necessary. Let's just see what happens when you plug in 0. So I plug in 0, I get 2 times e to the 0, which is 1. So I get 2 times 1 minus 1 times, it really doesn't matter what the rest is, but it is 3 times 1. So I get the 0 on top. See what happens if you plug in 0 on the bottom. I get negative 3 times e to the 0, which is 1, times 0, sorry, plus, that plus is super important, 0 times 3 times e to the 0. So here we end up getting 0 over negative 3, which is 0. This is a good kind of reminder to not abandon ship too soon, in that I looked at the top part, I was like, oh, the top part's 0, it's probably going to be 0 over 0. but it wasn't. So make sure when you're plugging in, you look at the top and the bottom, because if you don't have an indeterminate form, then you usually just have an answer. Cool. So we got 0. All right. So the rest of the indeterminate forms are what we call um, the exponential indeterminate forms. And probably my favorite example of an exponential indeterminate form is, yeah, I like that one, is the following. The limit as x approaches, which one do I like the best here? That doesn't matter. It does kind of matter. I'm just thinking about which one I ought to do this. Yeah, let's do it that way. Limit as x goes to infinity of 1 plus 1 over x to the x power. And you might already recognize this limit. We've talked about it before back when we talked about the derivative of e to the x. This limit is e. We're going to show it now, though, using L'Hopital's rule. And, I meant to look at the notes from the class to see how. So there's kind of two schools of thought on how you do a limit like this. First of all, I should talk about what's happening here. If I plug in infinity, I get, now this is where I want to remind you, I'm not actually going to get 1. But if I plug in infinity, I get 1 over infinity, which is close to 0. 1 plus a number close to 0 is close to 1. We write 1. The exponent is infinitely large. But again, what I really want you to be thinking of here is you have a number close to 1. In this case, a little bit bigger, although smaller would also be fine. A number a little bit close to 1 multiplied by itself a lot of times. Now, here's why this is important to think of it this way. If it was actually 1, 1 times 1 times 1 times 1 forever is 1. But if it's a number that's infinitesimally bigger than 1, multiplied by itself a lot of times, you overcome that being close to 1, you break away from 1. You move away. You're going to not, this limit is definitely not going to be 1. So we really don't have 1 times itself much time. You have a number just a tiny bit bigger than 1, multiplied by itself a lot of times. Also, I encourage you to graph this if you have a chance on Desmos. You'll see it's definitely not 1. But so here's the question though. And let me ask you, has your teacher talked about an example like this yet? Okay, so there's 2 ways to think about doing a problem like this. You can either do it this way. We're going to rewrite it as the limit as x goes to infinity of e to the natural log of 1 plus 1 over x to the x. And then you can either deal with this whole thing the whole way, but what most people end up doing is they say, well, first of all, this is going to equal, the e part here is not really important. I mean, it's important, but it's not affecting anything other than the overall value. The variables are all here, so you can rewrite this as e to the limit as x goes to infinity of the natural log of 1 plus 1 over x to the x power. It's kind of like how when you take a limit of a function, you kind of just pass the limit through to the inside part, and then you plug in the value to the inside part. What I mean by that, in case what I'm saying sounds unclear, if you have the limit as x approaches 9 of the natural log of the square root of x, well, you're really just plugging in 9. But the actual thing you're technically doing when you do that is you're rethinking of it as the natural log of the square root of the limit as x approaches 9 of x. As long as the functions that you are using are continuous functions that are defined, at least wherever we're worried about, the limit can kind of travel through the continuous function to the inside part. That's what's happening here. So what people usually do then is say, well, I'm just going to ignore the e part for the whole process. I don't want to write e to all this stuff the whole time. What I like to write is I like to say that my answer is going to be e to the something, so that I don't forget about it. Because I've seen lots of students do it this way and then forget to say that their answer is actually e to the whatever they got. So we're going to then say our something that we're trying to find that we're going to plug in right there is equal to the limit as x goes to infinity of the natural log of 1 plus 1 over x to the x power. And then at the end of the day, whatever we get this equal to, let's say it was 5, our actual answer is going to be e to the 5th power. So then here's the process. And this is always the process after you've done this natural log thing. The exponent part gets to come down in front, and then usually comes down to the denominator as its reciprocal. So we're going to rewrite this as the limit as x goes to infinity of x times the natural log of 1 plus 1 over x. At this juncture, we have an infinity times 0, right? X is going to infinity. Natural log of 1 plus 0 is going to the natural log of 1, which is 0. And then we bring the less terrible part to the bottom, clearly the x, not the natural log of grossness. So we have the limit as x goes to infinity of leave the natural log of 1 plus 1 over x on top, divide by the reciprocal of x, which is 1 over x. This, by the way, is one of the reasons I said you really want to get comfortable just knowing the derivative of 1 over x is negative 1 over x squared, because it comes up relatively frequently, especially in these examples. So then we can use L'Hopital's rule, because the numerator is going to 0 and the denominator is going to 0. Right? On top, you have the natural log of almost 1. On the bottom, you have almost 0, essentially 0 over 0. So now, using L'Hopital's rule, geez, forgot to write the limit. It's terrible. Limit as x goes to infinity of, okay, the derivative of the 1 over x is negative 1 over x squared. I always like to start with the easier thing first. I know it's like often we do top first, but like the easier part is just the easier part. Do that first. Now, in the numerator chain rule, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. The derivative of 1 is 0. The derivative of 1 over x is again negative 1 over x squared. And look at that. How lucky are we? The negative 1 over x squared is going to cancel the negative 1 over x squared. It's kind of great. It happens a lot. So now here's what we're left with. The limit as x goes to infinity of 1 over 1 plus 1 over x, which is going to be 1 over 1 plus 0, which is just 1. Which means our final answer is e to the 1. So the actual limit we were looking for as x goes to infinity of 1 plus 1 over x to the x power is e to the 1, or just e. Kind of cool. I think it's kind of cool. Thank you. So there's kind of a more generic idea of this. And what I want to say is this kind of limit comes up pretty often. In fact, in future classes, you kind of don't even show all this work. You're just like, cool, I know what it's going to be. So, for example, someone could ask you, like, what's the limit as x goes to infinity of 1 plus 3 over x to the 2x power? And with experience, you'd be like, cool, that's going to be e to the 6th. And here's kind of we're going to show the work still, but here's the idea of how I'm getting that e to the 6th so easily. I'm going to write it as the limit as x goes to infinity. Here's what I really want. 1 plus a thing. And I really, really, really would like my power to be the reciprocal of that thing. Right? That's what I had over here. I had the 1 over x and the reciprocal of 1 over x. So I'm going to write it. I'm going to write x over 3. That's not actually what I had. Right? I had 2x. So I still need to multiply that x over 3 by 6. So that 6 times x over 3 is really 2x. And then I'm going to do one more rewrite. I'm going to rewrite this as the limit as x goes to infinity of, check this out, 1 plus 3 over x to the x over 3, all to the power of 6. Because when your powers multiply, you can write them as a power to a power. And then I think I could convince you all that this part inside here, that limit's going to go to e. Because it's the same sort of thing. You have a 1 plus a thing. In fact, here's what if you really wanted to get technical about it, you could do like a change of variable and say, I'm going to let y equal x over 3. Then 1 over y is equal to 3 over x. And then I really have the limit of 1 plus y to the 1 over y. Nope, sorry, I got that backwards. Apologies. I have the limit of 1 plus 1 over y to the yth power to the sixth. And if x is going to infinity, x over 3, which is y, is also going to infinity. So look, I have exactly the same thing I had before, except now it's raised to the sixth power. So it's e to the sixth. People do that kind of like, it's a little hand wavy, but not really. We're still going to do this one, but I just want to point out, when you have one that looks like this, it's pretty not terrible to kind of figure out what the power is going to be. In fact, the more general statement, just so you know, is that if you have the limit as x goes to infinity of 1 plus a number over x to the x, you're just going to get e to that number. Kind of cool. All right, let's do it. Yeah, we should do it. So I'm going to tell you, though, it's going to be a little boring in that we pretty much already did it. So if we're going to do this limit here, same process. For any of these exponential forms where you have something with an exponent, you're always going to do the e to the natural log. You have to. There's no other way to really attack it. So we're going to think of this as the limit as x goes to infinity of e to the natural log of 1 plus 3 over x to the 2x power. And then the limit comes through, and we write it as e to the limit as x goes to infinity of the natural log of 1 plus 3 over x to the 2x. And then same stuff we did before. We're just looking at the boxed part. So it's going to be the limit as x goes to infinity of the natural log of 1 plus 3 over x to the 2x power. The 2x comes down in front. I feel like you can skip this intermediate step here sometimes. Instead of doing the 2x times the natural log of 1 plus 3 over x part, you can skip straight to saying it's the limit as x goes to infinity of the natural log of whatever on top divided by the reciprocal of 2x, so 1 over 2x on the bottom. Then we use L'Hopital's rule. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. Okay, check this out. The derivative of 1 over x is negative 1 over x squared. The derivative of 3 times 1 over x is 3 times negative 1 over x squared. Or as I would probably write, negative 3 over x squared. Similarly, what we have down here is 1/2 times 1 over x. And the derivative is going to be 1/2 times negative 1 over x squared. Oh, look, the negative 1 over x squared get to cancel again. That happens a lot. Look what we're left with. The limit as x goes to infinity of 1 over 1 plus 3 over x times 3. Dividing by 1/2 is like multiplying by 2. And we end up getting exactly 1 over 1 plus 0 times 6, which is 6. Which means our final answer is actually e to the sixth. So the limit as x goes to infinity of 1 plus 3 over x to the 2x power is e to the sixth power. So back to the list of exponential forms for just a second here. Where'd you go? I had you. There we go. So there's 3 more exponential indeterminate forms. One of them is 1 to the infinity. The other 2 are 0 to the 0 and what's the other one? Infinity to the 0. Why these 3? Here's why. Because when you take the natural log of any of them, you get something that ends up being a 0 over 0 or infinity or infinity. Let me show you. I see. So let me just point out. For this one here, if you take the natural log of a 1 to the infinity, again, this is kind of silly notation, so don't pay too much attention. But you bring the infinity down, you get infinity times natural log of 1, and then you bring that down to the denominator as it's reciprocal, you get the natural log of 1 over a 1 over infinity. But that's a 0 over 0 type. Similarly, for 0 to the 0th power, if you take the natural log of 0 to the 0 comes down in front, you get 0 times natural log of 0. Bring the 0 down to the bottom, you get natural log of 0 divided by 1 over 0, but that's a negative infinity over some sort of infinity type. Right, because natural log of 0 goes to negative infinity, and 1 over 0, depending on the type of 0, is some sort of infinity. Same deal here. The natural log of infinity to the 0 comes down in front, goes down to the bottom as it's reciprocal, and the natural log of infinity goes to infinity, and 1 over 0 is some sort of infinity. That's why these three types work out to be indeterminate forms. Because when you take the natural log, you either end up getting a 0 over 0, but you can only really get a 0 over 0 if you have a natural log of 1 on the inside and a division by 1 over something big on the outside. Or you get an infinity over infinity one of these two ways, by either getting a natural log of 0 divided by 1 over 0, or a natural log of infinity divided by 1 over 0. You don't have to know this. I just think it's interesting. And also it's not that it's not worthwhile, it's that you don't have to specifically know it. You do have to kind of know that these three forms are the ones that require this process. Any other kind of weirdness you might encounter doesn't. So like a 0 to the infinity is fully determined. If you multiply 0 by itself, or something really close to 0 by itself, a lot, you're just going to get 0. So practice. Time is it? Okay, we got 10 minutes. Cool. 9 minutes. Okay. Let's look at some other things. Sure. Let's look at the limit as x approaches 0 of sine of x to the x power. Definitely a 0 to the 0 power type. So we got to do the log thing. Now, some people just don't even write the e to the natural power. Some people, instead of doing what they've done before, they say something like, let's look at or examine the limit as x goes to 0 of the natural log of sine of x to the power of x. And then off to the side say, we know our answer will be something. This feels like too much writing. Will be e to the whatever we end up getting, right? This is going to be something here. And that, whatever that's equal to, is going to go right in there. I feel it's kind of silly. I don't like doing it that way, but some people do. So, usual steps. Bring the power down and then bring it down to reciprocal. So here, we're going to rewrite this as the limit as x goes to 0. Again, I think you should get in the habit of being comfortable with skipping this step because it feels like a lot of writing and going straight to the limit as x goes to 0 of the natural log of sine of x divided by 1 over x. I think that's a pretty fine step to just go straight from there to there. If necessary. Sometimes your power will be something that, well, in fact, we'll just do one. So let's see. So now I can use L'Hopital's rule because my natural log of 0 is going to negative infinity and my 1 over 0 is going to some sort of infinity. I'm not really worried about. I should be worried about. This should be a limit as x approaches 0 from the right. Why do I need that? Kind of I mean, need is maybe an overstatement here, but sine of 0, if you're approaching 0 from the left, sine would be slightly negative. You can't take the natural log of a negative thing. Another way to think about this though is no, that's it. That's all I want to say. So, L'Hopital's rule. Limit x goes to 0 from the right. Derivative of the top is 1 over sine of x times the derivative of sine of x, which is cosine of x, divided by the derivative of 1 over x, which is negative 1 over x squared. That looks terrible. But it's not as terrible as it looks. Let's rewrite it. I don't believe it is advantageous here to write cosine over sine as cotangent. I think leaving things as fractions is going to be more helpful. So I could either write this as the limit as x goes to 0 from the right of I have cosine x over sine x, and then instead of dividing by 1 over x squared, I'm going to multiply by x squared over -1. I don't really care where the negative goes. And then that's actually, I should have just written this one fraction. Limit as x goes to 0 from the right of x squared times cosine x over negative sine of x. Writing this as x squared times cotangent or negative x squared times cotangent would mean I wouldn't be able to use L'Hopital's rule because it wouldn't be a fraction. So leaving it as cosine over sine, I think, is definitely required here. Plugging in 0, we do get 0 over 0. Right, 0 on top, over 0 on the bottom. So now, L'Hopital's rule again. Mm-hmm. You could avoid using L'Hopital's rule here if you wanted to. You could, well, I'll say that afterwards. Using L'Hopital's rule will also be just fine. The derivative of the bottom is negative cosine of x. Product rule on the top, you're going to get 2x times cosine of x plus x squared times negative sine of x. And if we plug in 0, we get 0 times cosine of 0 plus 0 times sine of 0 over negative cosine of 0, which is -1. We get 0 divided by -1, which is 0. Be careful. It's easy to forget that our answer isn't 0. Our answer is e to the 0, which is 1. Right? Right? So don't, right? The problem with these problems is they get so long, you forget what you did in the beginning. In the beginning, we said, oh, yeah, right? We're trying to find the limit of sine of x to the x. We found the limit of the natural log of sine of x to the x. To undo that natural log, we have to do e to the stuff. Oh, yeah, e to the result is 1. Interestingly, most, not all, but almost all of the 0 to the 0 types end up being 1. There are some rare exceptions, but most of them do end up being 1. It's kind of weird. I wanted to point out here, though, if you wanted to, you could have gone a slightly different way here. You could have said, I'm going to write this as the limit as x goes to 0 from the right of x over sine of x times x cosine x over -1. This part here, the x over sine of x, the limit of that is 1. And for this remaining part here, 0 times 1 over -1 is 0. You can totally have done it that way. It's totally valid. And then your answer is still e to the 0, which is 1. I think this whole kind of thing, I think this is why I don't like writing it like look at this and then this. I think it's better to write the e to the natural log of your thing. I feel like it's a better kind of reminder of the fact that you have to do the e to the part at the end. Sure. How much time have I got? 3 minutes? Yeah, let's look at one more. Let's look at so question. Yes, so let me show you in this example what I mean. So let's look at one more example. The limit as x goes to 0 from the right again of sine of x to the 1 over x. So now instead of a 0 to the 0 type, we have a 0 to, I feel like 0 to the infinity is not what I want here. That's not one of my indeterminate forms, right? No, definitely not. This is not indeterminate. Indeterminate. The answer is just 0. Now, you might still need to show some work here. Yeah, here is the answer 0? Yeah. Yeah. Here's the work I would show. I would write this as the limit as x. I'd still do the e to the natural log thing. E to the natural log of sine of x to the 1 over x. Now check this out. When I bring down the 1 over x in front, I am just going to write the whole thing because it's going to not require the other process. So I'm going to write e to the 1 over x times the natural log of sine of x. I'm not so much going to bring 1 over x to the bottom as its reciprocal. I'm just going to say, well, the x is already in the bottom, right? So what I really have here is the limit as x goes to 0 of e to the natural log of sine x over x. Okay, let's actually plug in and see what happens. We get e to the, well, the denominator of that exponent is very small and positive. And as you guys have correctly said many times here, natural log of 0, okay, right? Because sine of 0 is going to 0, and natural log of 0 goes to where? Where? Negative infinity. Okay, if you have a super large negative number divided by a super small positive number, what kind of thing do you have? Was it negative or positive? Negative. Is it really big or really small? Sorry, really negatively big or really close to 0? If you have negative a billion divided by 0.001, huge, negatively huge. This is negatively huge, right? Infinity over 0 is not indeterminate. Infinity over 0 is infinitely large, and you just have to determine if it's positive or negative. This one's negative. So what you really have here is e to the negative infinity, or which I don't love just going straight to saying that's 0. I like to take one additional step and say, hey, that's 1 over e to the infinity. That's 1 over a big thing. That's going to be small. Or as I said before, if you have 0 times itself a bunch of times, you're going to get 0. But I think you probably need to show work like this here. And I guess I'm out of time, so I won't do one more example. Next week, we'll talk about optimization, which in many ways feels similar to the process of related rates, where it's a bunch of kind of, you're setting up a couple equations, you're doing some things, you're taking some derivatives. It's a different process, but there are some similarities. Now I'll be over in El Centro as usual.